Hi, everyone. My name is Rachel, and I'm from Caltech, working for Professor Jose Andrade in the Complex System Modeling Group, the Cosimo Group. And today I'll be talking a little bit about my project focused around modeling multi-block systems, predicting seismic performance using Lcm. So as the name indicates, multi-block systems are those consisted of blocks, for example, the Egyptian pyramids and ancient Greek temples. Some recent applications of multi-block structures include radiation shielding system using giant concrete blocks. Particle physics labs like the European Organization for Nuclear Research, abbreviated CERN, they use such multi-block structure to shield radiation from their particle colliders. However, all multi-block structures suffer from the problem of seismic instability. That is, in times of an earthquake, such structure might collapse. So CERN's protected structures are no exception. And not only that, all concrete configurations used at CERN do not have any joint connection or any additional metal bracing system to resist lateral forces that might induce during the seismic activities. Therefore, it is necessary that CERN examines the structural stability of such concrete structures ahead of time. So simple configurations might be analyzed using analytical methods or simply be put onto a shake table for tests. But complex configurations simply cannot be tested one by one. And therefore, we would need the usage of numerical modeling. So the idea is really to benchmark the models against some experimental results. And in the future, we can use such validated numerical models to simulate the response of any concrete structures, and no matter of its complexity or its scale. So with this idea in mind, CERN carried out an experimental campaign at U Center. They tested the dynamical response of 4 simple configurations of multi-block structures on a shake table. Both optical markers marked in white here, and also as well as the accelerometers are attached on each of the block in order to obtain the acceleration and displacement profile of the blocks. Those data will later be compared with my simulation results. So we used level set discrete element method as the numerical tool. It's a variant of the classic discrete element method capable of simulating the kinematics and mechanics of discrete systems. With level set functions as a geometric basis, LSTM can simulate any arbitrary shaped objects, of course, including the blocks. So the level set function calculates the sign distance from an arbitrary point to the nearest surface of the grain. Together with a set of surface nodes around the grain, we can easily calculate the penetration and impose surface elasticity relationship onto the pair of contacting blocks. This is the simulation results of LSTM versus experiments across a range of parameters. The displacement of the block at each level is plotted in red line. The dashed line represents the actual experimental results. And from the comparison here, we can see that LSTM results match with the experimental ones closely. Note that the experimental results only shows one set of data, but the simulations are ran on a range of parameters, hence the thicker envelope here for the red line. And this is the comparison of another configuration tested. Again, we see that LSTM results show remarkable resemblance to the experiments. So now that we have confidence in our numerical modeling, we can use it to simulate any complex structures, even actual concrete structures that is being used at CERN. So this is just an example of the type of things that this model can do. Experiment only gives us one set of data point, but when we use the model, we can capture the wealth of responses by playing with different variables of the blocks. We can even include defects of the blocks, and therefore the model can show a range of possibilities, and it really takes the complexity to the next level. So the summary here, LSTM simulations can accurately capture the dynamic response of multi-block structures. The level set discrete element method can be used to predict the seismic performance of future multi-block structures. And the simulation results can be used to engineer more complex structures in the future. And that concludes my talk. Thank you. I'd be happy to take any questions.
Any questions for Rachel?
I have a quick question. You can just ask it short. I'm curious how they account for energy dissipation when they impact the environment. Do they have a coefficient of restitution or exactly?
How do you account for energy dissipation? You have a coefficient of restitution.
We do. So we implement a local damping in the code to help stabilize the system, but really it should have no effects to the actual performance of the blocks.
I have a quick question. Do you foresee any impacts of different configurations of the stack structures on the matching of the results?
Well, actually, what do you mean by different configurations?
So we have a configuration of 2 towers. What if it were like multi-width towers, like double wide?
Like you mean in terms of experiments as well as simulation results? So what I'm seeing in the experiments, as well as the simulation, is that as we go higher in those towers, the displacement will be larger, which is reasonable and natural, right? Because as we go higher in the blocks, it is natural to anticipate more rocking mechanisms in the experiments as well as in simulations. And also
Professor Lcm, did you have a question?
Yeah, I have a quick question for you, Rachel. So the results you show, you have a nice comparison where the experimental results do not have residual deformation. Do you have any, do you look at any case where you may have some permanent deformation at the end of the record?
Thank you for the question. We do have residual displacements in both the simulation results as well as in experiments. It's just that due to the scale of those, the data, it's like 0.05 meters for the spike here. So it's really not noticeable. But yeah, it is possible to observe residual displacements in both the simulation and the experiments, if that answers your question.
Yep, very nice. Thank you.
Oh,
thank you.
We have one more. Sorry, Rachel.
Are they intending to test this on simulation to collapse?
Are you intending to test this simulation to collapse?
No, because the idea is really to benchmark the numerical model so that we can use this numerical model to simulate complicated concrete structures that cannot be put onto a shake table. For example, those actual protective structures that they're using at CERN. So we do not test it till failure. And also in actual experiments, we have a protective metal bracing system to make sure the safety of those test specimens. But those protective metal bracing systems are designed such that they will not engage with the performance of the blocks in the tests.
Sorry?
That's we can surely know that, but we are at the shake table here. We have the collapse.
Oh, we're offering to test to collapse at Richmond Field Station. If you want to collab.
Yeah.
Yeah, if you would like to use the Richmond Field Station shake table to test things to collapse, Arpit Nima will help you with that.
I think
Okay,
Arpit is I hear Arpit asking the question, if she breaks the table, you're gonna pay for it.
I see. I guess I'll be careful with that.
Thanks so much, Rachel.